Could you imagine living in the modern world without computers, like your phone or the laptop in front of you? Things that we take completely granted for today, like being able to message a friend thousands of miles away in the blink of an eye, were unimaginable just a few decades ago. But standard silicon technology is reaching its physical limits. To build the computers of tomorrow, we need entirely new materials. This brings me to a fascinating material called tantalum disulfide. It belongs to a family of materials that can switch the electrical properties on command, acting like a quantum light switch. In this material, electrons don't just flow like a liquid. At certain temperatures, they freeze into highly organized repeating patterns called a charge density wave. In this state, the material instantly switches from a conductor to an insulator. In bulk three-dimensional crystals, we have to freeze the material to cryogenic temperatures, nearly the temperature of outer space, to get this perfect state. But my research question is, what kind of exotic properties does two-dimensional tantalum disulfide exhibit at room temperature? We hypothesized that by stripping away the extra dimensions and removing the friction of neighboring layers, we can force this perfect frozen state to lock in at room temperature. So, how do we study a material that is only one molecule thick? First, we use a deceptively simple technique called mechanical exfoliation. Using specialized adhesive tape, essentially high-tech Scotch tape, to peel apart crystals down to a single layer of atoms. Because these single layers are incredibly sensitive to air, we perform this inside of an argon-filled glove box and immediately sandwich the tantalum disulfide with a protective layer of a material called HBN. To see what the atoms are doing, we use Raman spectroscopy. By shining a low-powered red laser at our sample, we listen to the atomic echo of its vibrations. Low energy photons are emitted from the material, and this energy difference between the incident light and the emitted light tell us about the energy of vibrations in the material. These vibrations act as a fingerprint, letting us know exactly when the atoms are frozen into that unique charge density wave pattern. If our hypothesis is correct, and we can stabilize this quantum phase transition at room temperature, the implications are massive. We are paving the way for next generation technologies like neuromorphic computing, building computer chips that process information like the human brain by freezing and thawing electrons on a molecular scale. By understanding the quantum rules of the 2D world, we aren't just observing physics, we are building the foundation for the next technological revolution. Thank you.